Okay, Newton's laws. We're doing force analysis very carefully. Oops. we want to know why things move the way they do. We want to be able to describe it. So we'd like to predict what will happen if I do that. How long will it take? How far away, vertically, horizontally, etc. How fast will it be going? In which direction will it be going, etc. To do this analysis, we've talked about kinematics. We just described the motion, and Galileo really kind of started that ball rolling. But Newton took the ball and ran with it. So we're going to look at this very carefully. And these concepts, they're tricky. So if we're not really careful to set it up, you'll think, oh yeah, I got that. You know, that's fine. I can do some problems. But then you hit the wall and make mistakes. And let's try to avoid that. And there's something very, very deep here. I mean, Galileo wrote his findings in common Italian and got in trouble and was on house arrest, continued his work. The work got smuggled out, and around the year Galileo died, Newton was born, he got a hold of that, and Newton took off and ran with it. It's very profound, and unless you really think about it, you can't fully get that, but you can get it, and so we'll work on this. We need the concepts of acceleration of some object that we want to choose to look at, the mass of that object, which is both the inertia and the property responsible for gravity in some mysterious, weird way. Force of any type from what I call the source object on R, or the receiver object. And so let's put those into context of Newton's 3 laws of motion. All right. Basically, it says, you know, why do things move or not move? And Aristotle, over 2,000 years ago, was thinking about this, and he did great work on lots of things, but he kind of got this wrong. I mean, some things were fuzzy right, but fundamentally wrong. For instance, he thought that things in heaven naturally move in circles, and things naturally go home and kick back and watch TV. So they go home and go to rest. They find their natural place. Natural order was a common theme. And so in our head, this concept of natural order makes sense, feels good, but the physical world doesn't care, as near as I can tell. And so some things about physical law really is not intuitive to our senses and our logic, you know, program in our brain. So let's try to see what makes sense and then what doesn't, so we can go beyond. Because these laws lead to even deeper laws of quantum mechanics and relativity. So they're cool. Let's get them straight. You can get them, though. Okay, so Newton's 3 laws of motion. There's Newton's first law, second, third. Let's talk about Newton's first law, giving due thanks to Galileo. I call it the law of equilibrium. I strongly urge people to call it the law of equilibrium, not the law of inertia. Well, see, it is not an issue of inertia, because inertia is one of the properties of mass, right? Or mass has inertia or resistance to acceleration, as we discussed. So the thing is, this law is true no matter what your mass is. Whether you're an elephant or a bowling ball or a ping pong ball, it doesn't matter. This law is true. So in fact, this is independent of inertia. Okay, it's independent. It isn't, people make a big mistake and think that because if you have more mass, you have more tendency to go forward. No, there's something deep about nature, space and time, such that you have a tendency to go straight. If you worry about warped space-time, we can build on this and follow the curves of space-time. Here's the law. Now let's take a look. It's the law of equilibrium. Equilibrium means, hold on to this definition, because again, when it's tricky, you just go back and retrain your intuition. Equilibrium is synonymous. You can either say that the acceleration of the object is 0, that's equilibrium. And that implies, this arrow, that the net forces on the object are 0. So there might be pushes and pulls. I mean, we can imagine an environment where there's no forces at all, but you better get off Earth, right? So we can imagine that there's no forces, but if there are forces, they're all here in balance. We'll talk about that in a moment too. Or you could say, if I know that the net forces are 0, if they add up to 0, taking account to the strength and direction, if they're 0, then I know that it can't accelerate, which we know is it can't change speed, increase speed, decrease speed, and it can't turn. So this is saying that although it seems like objects will come to rest, you push something, it'll stop. That's our intuition. You push something, you expect it to stop. This is saying if it's moving, it'll keep moving, if this condition is true. So if you know the acceleration is 0 just by looking at it, it's not changing speed and it's not changing direction, then you can, without any calculation, know what the net force is. I know the net force is 0, I don't know what each individual one is. Or, conversely, if you know that the net force is 0, you can predict that it will not change speed and will not change direction. This is called a biconditional. Okay, so that's what equilibrium means. Now, one big mistake, write myself a little note here. One big mistake here is to think that that means you're not moving. Our intuition is that. But there's two cases for equilibrium. There's static equilibrium, and that means the object's not moving, and in this case, it's not going to start moving. Okay, so that's just anything at rest. Me, now, you, whatever. Okay, this board, everything around us, right? That's just static. Static equilibrium, fine. But the tricky thing is here, it's dynamic equilibrium. So it can be moving. The velocity of that object is not 0, but it is constant. Okay, so our intuition has to kind of reframe, like objects will go forever. Forever. They can't turn. It's not natural that heavenly bodies go in circles. They go straight. Right? You take off the forces of moon and it'll just go straight off whatever direction it's going at that moment. Remember, velocity is tangent to the path. You go off in that direction. Take off the force of gravity, Earth will just float off into space, right? Everything's going straight in whichever way, right? So if the net force is 0, the acceleration is 0. You might be not moving, then you won't start moving. But it also is true, and maybe, again, we get mixed up with time. So it might have taken something to get it moving, but if we're just looking at it now, we don't worry about what happened in the past, and maybe it's going to hit a tree, fine. But in this process, while it's just coasting along, in a straight line, no turning, constant speed, then we have to have the net force is 0. Now, there might be forces. Again, you can imagine this floating in space, or you can imagine something trucking along. Speaking of which, if you have a large truck, if it's lost its brakes, it isn't going to stop on its own. Things won't stop on their own. They won't turn on their own. Think about this with ice. You're driving along. You hit this perfect sheet of ice. You hit your gas pedal to get out of the ice. That'll spin your tires, but it won't make you speed up. You hit your brakes. That stops your tires, but the car keeps on going because you haven't got that friction, traction on the surface, that interaction. Remember, force is an interaction from other things. Okay? So turn the wheel. You'll still go straight. Let's demonstrate this here in just a second. So that's what the first law of motion is, and it really can be a bit tricky. So let me do another bit on language here and show you that if you use careful language, what will happen is it'll draw you into much more subtle awareness, particularly when your intuition is going left and what's really happening is going right. Let's straighten this out. So, law of equilibrium. It's not the law of inertia, really. It is called the law of inertia. This is it. Static equilibrium or dynamic equilibrium. Now, in this case, we have the net forces from all sources on whatever receiver, a net force comes from adding up mathematically the force vectors. We add those up mathematically. And then if that's 0, fine. So if that's 0, the important thing here is mathematically the forces cancel. But let's not say that. Remember, think physics, because that's going to restrict the math. Math is a beautiful thing, but we want to restrict it to this case. So physically, the forces balance. Please use that word. Forces don't cancel, they balance. Do this. Take your right hand, put it on your right cheek. Take your left hand, put it on your left cheek. Now squeeze. If you push the same amount, they're in opposite directions. Mathematically, they'll cancel, but they don't really go away. It's not like this is the same as this. That's different than that. That's not canceling, that's balancing. And it makes a difference. If you don't think in those terms, you don't have buoyancy, you can't float ships, you look at force couples, all kinds of things. The forces don't go away. I mean, maybe you get tired and go, whatever, I'm not getting it done. Then they're gone away. Canceling is a mathematical term. Balance is the physics. In this case, forces are balanced. You will not accelerate. It doesn't mean you aren't moving. Maybe you got moving from another force. Okay, cool. Real quick here. How are we doing on time? All right, so let's take a look. So point here. Ping pong ball this. In space, or if I can get rid of all forces, these both will want to go straight equally. It's not like one wants to go straight more than the other. Now, one will be harder to turn, one will be harder to speed up, one will be harder to slow down, but that's Newton's second law. That's Newton's first law. Everything independent of inertia wants to go straight forever. Strange. It's not our intuition. Okay, so take a look here on the table. We'll see this. We've got objects, and I kind of do this little thing. We'll test it out and see if that works. Wait a minute. It seemed to go home and stop. Maybe stop is its natural motion. Yeah? Ooh, it stopped even faster. Maybe if I smooth out the surface. So the way to think about this is a hockey puck or something on ice, right? It's gonna keep on going straight. It won't turn, it won't slow down. It might slow down a little bit, so smooth out the ice more, smooth it out, put it on an air track, whatever it is. It'll keep going. Something's making this stop. Okay. So yes, something had to, it's now in what kind of equilibrium? Static equilibrium. I push it, Newton's second law, we'll get to that. And then once it's moving, it should move forever. Put it on wheels. Get a better result there. All right, cool. Let's put it on wheels. Yeah, it's still slow down. Push it hard. Go farther, right? So maybe there's some friction. We'll talk about that within the wheel. So I smooth that out. The more I smooth that out, the more I get rid of or balance all the forces, the more it'll continue on forever. If it's not perfectly balanced, this won't happen. If it is perfectly balanced, it will. So one thing that really confuses our mind, and it does, so there's nothing wrong with that, is turning. Uniform circular motion. All right? Is it accelerating? If the speed is constant, at least for a short period of time here, the speed is constant, it's still turning, so it is accelerating. Whether it be moon around Earth, Earth around sun, or a satellite, or whatever it is, a car taking a turn on the road. That is accelerating because it's changing velocity. That is, it's changing direction. But something has to cause that to happen. And so if there are no unbalanced forces, if you look at this, there's a ridge there, right? If I take away the ridge, what will it do? Okay, we're going to work on this, but try now. If there's no unbalanced force. Hello. All right, so it goes straight. It goes straight. Nothing pulled this out. That's what things want to do. That's another way to say this. What do things naturally do? They don't naturally go home and stop. They don't naturally in the heavens behave differently and go in circles. So Aristotle was wrong about that, but he contributed. We stand on the shoulders of giants. And so, oops, what do things do? They just keep on going, right? I wanted it. I willed it. Please come back. No, they do what they do. And what things of themselves, independent of inertia, what they do, if they're moving, they keep on trucking. So have that idea. Acceleration being zero does not mean v is zero. But if you start out at rest, you'll stay at rest. If you start out or get started in motion, you keep on going. And if this condition is not satisfied, balanced forces, let's just get rid of this. Balanced forces, if that's not satisfied, of course you will accelerate. And if you accelerate, that means, or the object R, receiver will accelerate, will either increase speed, decrease speed, and or turn. And that's Newton's second law, and let's do that on the next video.